Hi, today I want to discuss about chemical kinetics. The first one, why we have to study this chemical kinetics. To know that, first one given is the feasibility of a chemical reaction which can be predicted by thermodynamics. When you perform a chemical reaction, that is possible or not, reactant convert into product proceed or not, that will be given information by the thermodynamics. You know that the reaction with the delta G, that is dg given here, that is meaning a delta G. So delta G less than 0, that is feasible at constant temperature and pressure. So delta G less than 0 or that is negative, that is spontaneous reaction, then reaction is possible to convert into product. So that indicating reaction is feasible. Next, B. Extent to which reaction will proceed can be determined from chemical equilibrium. What extent that reaction complete? For example, we know that is reactant convert into product. What extent it complete? 50% reaction complete or 80% reaction can complete or 100% reaction can complete. That we can know from the equilibrium. Now next one, speed of reaction. The time taken by a reaction to reach equilibrium or to complete, that will be known from the chemical kinetics. That will be known from the chemical kinetics. So these three are very important for us to know the reaction when convert reactant to product. So first one, what is required? Feasibility of reaction means thermodynamics required. Extent of reaction meaning a chemical equilibrium required. Speed of the reaction or rate of the reaction we have to know mean that is chemical kinetics required to reach the equilibrium or to complete the reaction. Along with the feasibility and extent to which a reaction complete is equally important to know the rate and factor controlling the rate of a chemical reaction for its complete understanding. We know that reaction feasible and what extent it complete, but we should know that equally to control the rate or what factor we can control to increase or decrease the rate of a chemical reaction. Therefore, we should know the speed or rate of the reaction. Next, for example, which parameter determine as to how rapidly food gets spoiled, how to design a rapidly setting material for dental filling. For example, we prepared food morning, then it will be stored maximum 1 day or next day. To store next day, what factors or what are the conditions we can provide, then it can be up to next day. That condition we should know. When we should know that? By knowing the rate of that food can get spoiled. If food can spoil in 1 day, if you know that, so within 1 day we can utilize. If you know that it can be protected or it can be, what do you call that, preserve the food up to 2 days, if you know that, then we can utilize in the 2 days. If we don't know that, then how we can utilize, that is difficult. That's why rate should be known. And here dental filling they given. So according to that, if anything tooth ache may be or something tooth may be spoiled, that is called some hole may be formed in the teeth, then we have to insert some material that is called dental filling. That material should be settled fast, then it will be converted to solid form. If we don't know how long it takes time to settle as a solid material, then filling of that material into the teeth is very difficult. Next, what control the rate at which fuel burn in an auto engine? For example, we start any motor vehicle, that is car or bus or something. So what rate it burn also we should know that. That is called mileage also. So 1 liter gives this much kilometer. So based on that we can move forward for a long journey. Next, all these questions can be answered by a branch of chemistry. So what is the this chemical kinetics definition meaning? Which deals the study of reaction rate and their mechanism is called chemical kinetics. So this is important for what is the chemical kinetics definition, which deals the study of reaction rates and its mechanism. The word kinetics derived from Greek word kinesis meaning a movement. Thermodynamics tells about the feasibility of reaction, whereas chemical kinetics tells about the rate of reaction. So already I told you that thermodynamics means whether the reaction possible or not. That decides the thermodynamics. Chemical kinetics, it gives information about the rate of reaction, how fast that reaction will complete. For example, we will take one example here. Thermodynamic data indicate that diamond shall convert into graphite. That is possible. So according to this one, diamond that convert into graphite, according to thermodynamics, it is possible. Now, in reality, it is convert like this? No, because its conversion rate is very slow. That change is not perceptible at all, meaning it takes millions of years. If it is convert, mean no one can purchase the diamond, because if today diamond purchase, tomorrow convert into graphite, mean that is totally loss. Therefore, we should know what rate that diamond convert into graphite. That's why study of the chemical kinetics is a very important. Now, diamond convert to graphite according to thermodynamics it is possible, but its rate is very slow. Therefore, most people think that diamond is forever. Diamond is not forever. It may also convert into graphite according to thermodynamic data. Kinetic studies not only help us to determine the speed or rate of chemical reaction, but also describe the condition by which the reaction rate can be altered or changed. So kinetics explain what is the, it determine the speed or rate of a chemical reaction or any process also. So if you know that speed or rate, then we can alter its rate or its condition. Then if condition change, it means rate also changed. So we don't want that some reactions are fast, some reactions are slow. Therefore, by controlling that speed may change. So fast reaction we can go to slow reaction, or slow reaction we can go to fast reaction by changing the conditions. Next, the factors such as concentration, temperature, pressure, and catalyst affect the rate of reaction. So these will affect the rate of reaction. Therefore, we can alter these conditions. What are that? One is concentration, temperature, pressure, catalyst. So again, detailed study of these effects we can study in further. Next, the macroscopic level, we are interested in amounts reacted or formed and the rate of their consumption and or formation. So what rate that is reactant consumed and what rate that reaction product or formed, that also we will understand by this chemical kinetics. At the molecular level, the reaction mechanism involving orientation and energy molecule undergoing collision also discussed in this chapter. So what way that molecule oriented and what energy required to convert into product, all these we will discuss in this chapter. Rate of chemical reaction. Based on rate of a chemical reaction, based on rate of reaction or speed of reaction, one, it is classified as fast reactions. Fast reactions are time may take in seconds or less than second. Time may take second or less than second. Example 1, strong acid and strong base reaction. One example for this, HCl plus NaOH convert into NaCl plus H2. Second example, precipitation reaction, that is called PPT reaction. Precipitation reaction. In this, one example is AgNO3 plus NaCl. This is convert into AgCl precipitate form plus NaNO3, and it is also known as ionic reactions. Ionic reactions are generally fast than the covalent reaction because just exchange of ion, that's why these reactions are very fast. And next, third one, any other example mean explosive reactions, very fast. Next, retinol vision, that also very fast. And next, fifth, photosynthesis reaction, that also very fast reaction. Like this, some example for fast reactions. Now, second one is slow reactions. What are the slow reaction? The slow reaction time taken is maybe in the day, or it may takes what you call week, or it may takes months, or it may takes years, like this. Example for this one, rusting of iron, that is called corrosion. Corrosion is one of the example for slow reaction. And second one is human aging, not only human, any animal age also, from 0 days to up to higher, up to 100 years. And next one, third one, ripening of fruits. Next, fourth one, hydrogen plus oxygen convert into H2O liquid. This is also very slow reaction on heating at high temperature. Next, another one, fifth, diamond convert into graphite, that also slow reaction. Next, sixth, conversion of that material into conversion of coal, because coal form in the earth crust millions of years it takes. So these are the some slow reactions. Next, third one, moderate reactions. In this moderate reactions, time take finite time, not very slow. This is called neither too fast nor too slow. These moderate reactions are easily we can alter their condition. So to alter the condition, which reaction required? Moderate reaction required. Fast and slow reactions are not useful. So in this chapter we'll discuss about the moderate reactions. It means the time taken finite time for this. Therefore, now for example here, the one generally organic reactions are moderate reactions. And next, in this one example, that is called inversion of cane sugar, sugar formula C12H22 O11 on hydrolysis in acidic medium. This will be converted into C6H12O6 plus C6H12O6. One is glucose, another is fructose. This is called inversion of cane sugar. Second one, ester hydrolysis. What is ester hydrolysis? We know that CH3COOC2H5. This is called ethyl acetate. This ethyl acetate simply called one ester. Then on hydrolysis, this will become in acidic medium CH3COOH plus C2H5OH. This is acetic acid. This is ethyl alcohol. So this is also one moderate reaction. For example, third one is 2HI convert into H2 plus I2. Next one, fourth, N2O5, that is 2 moles, convert into N2O4, that is 2 mole, plus O2. All these reactions are which one? Moderate reactions. So now, rate of reaction, important for board level. What is the definition of rate of reaction? Rate of reaction meaning what is that? The change in some variable per unit time. This is in general for anything applicable. For example, a runner travel or run from this starting point x1 distance, this is a x2 distance. For example, this is a person now like this traveling, running to this end position. Here time is t1 and here time is t2. Therefore, its rate can be explained as change in some variable mean distance. Change in distance by change in time. Therefore, rate is equal to generally uh, what do you call that? Change. Change mean always you have to remember final minus initial. Therefore, I can write that rate, the final distance is the x2 minus initial distance x1 and time is t2 final, that is, and minus initial. This is called uh, rate with respect to a person when running from starting to ending point. Now, rate of a chemical reaction, that is rate in general, rate of a chemical reaction. So, how to answer this? Now, the change in concentration of reactants, reactant one is a reactant, more than is one is a reactant, that's why reactant in s is in bracket, or products, here also same, change in concentration of reactants or product per unit time or with time, that is called rate of a chemical reaction. This can be written in the board level definition for rate of reaction, very important. This is what is the rate of reaction. Otherwise, some particularly with respect to reactant or with respect to product, that can be written as. So now rate of chemical reactions are also written as the decrease, the change mean what is that here? With respect to reactant, the decrease in concentration of reactant, one is there mean one, more than one is there mean plural. So change in concentration of, you can write any one of the reactant also. Change in concentration of any one of the reactants, one or any one change also, not only all together change, any one change also reaction rate alter, I mean change, or increase in concentration of any one of the products, that is called rate. Now, for example, I am writing one reaction here, reactant convert into product. Here, T is equal to T1 time, generally starting time 0. Then reactant concentration, I am considering R1 concentration. Product concentration, I am considering P1 concentration, generally product not formed at the T equal to 0 time. Next, T is time equal to some time, that is a T2 time. Then this is I am considering R2 concentration. This is I am considering P2 concentration. But R1 to R2 concentration, what happened? Decreases because it is 100%, then R2 somewhat decrease after some time because reactant convert to product. And P1 to P2, what is that concentration? Increases. Therefore, R1 is greater than R2 and P1 is less than P2. That you have to remember. Now, rate is equal to, what is a rate? A rate is equal to change in some variable. Now, with respect to reactant, I can write final minus initial mean. What is the final here? R2 concentration minus R1 concentration. Already we know that R1 is lower than the R1. Then what sign you will get? Negative. So listen first. Here I will write the time. Then here T2 time minus T1 time. So overall you will get a negative sign. Rate is generally a positive quantity. Rate is positive quantity. Therefore, we have to multiply with a negative sign, this one. So why this negative? This negative indicating here reactant concentration decreases. Therefore, to make rate positive, multiplied with negative sign, that you have to remember. Next one, in this reaction, what I can write now? Rate simply now, once again I am writing here, minus R2 concentration minus R1 concentration divided by T2 minus T1. Concentration unit, what is that? Mole per liter. Time unit generally will take in the second. Therefore, it can be mole liter inverse second inverse. Mole liter inverse second inverse. In case pressure is there, instead of this one mole per liter, I can write, if gaseous reactions are involved, atmosphere second inverse. This is for gaseous reaction. Similarly, with respect to product, this is with respect to reactant. Now, with respect to product, what will happen? Rate is equal to final minus initial, then final is P2 concentration minus P1 concentration. Already we know that P2 is higher than the P1, therefore positive value only you will get in the numerator, denominator T2 minus T1. So in this case, same unit will come, mole liter inverse second inverse. In case gaseous reaction is there, that is atmosphere second inverse. So now in this one case, time is 0. In this case, P1 is 0. Then you put 0 only, no problem, before I given in the equation. So now we know that rate with respect to reactant and rate with respect to product, that is called reactant respect to what rate the reactant consumed, and with respect to what rate the product are formed. So rate generally positive term, therefore we multiply it with the negative sign the reactant, but in the product anyway it is positive only there, no need to multiply or no need to write. If you want, you can write here positive, but nothing written also, that is a positive quantity. So now we know that what is the rate of disappearance, rate of appearance. So simply it is called, with respect to product, mean rate of appearance. Rate of appearance, or it can be say rate of formation. This can be called rate of disappearance or consumption. So now this can be explained with the graph also. This graph is explained here, time and concentration. Time and concentration, reactant concentration generally decrease and product concentration is increase. This is for reactant convert into product 1 mole 1 mole. That's why equal proportion reactant decrease and increase. So this is a concentration here increases and time here increases. In case I am taking here this example, N2O5, that is 2 mole, gives rise to 2N2O4 plus O2. For this can be explained as concentration versus time. This can be reactant is like this decreased, and product, two products are there. one product is like the same proportion increase. Second one, this one if you consider here 2 mole, here 2 mole, same proportion decrease and increase, but this is 1 mole is there, therefore this will be less than that one. This is with respect to O2, this is N2 O4 respect to this is N2 O5. So according to stoichiometric also the graph representation will be changed. The next class we will discuss about the average rate and instantaneous rates, and next we will discuss about the initial rate also. Now here important what is that in this one, rate of reaction definition important, you have to study the rate of reaction definition and units of rate of reaction. So rate unit once again I'm writing here mole liter inverse second inverse, otherwise mole per liter is known as a molarity second inverse. And next one for gases, this is called atmosphere or bar second inverse. And next, this time may be nothing given in the question will consider second, therefore second inverse, or it may be minute inverse, or it may be hour inverse, or it may be day inverse, or it may be week inverse, or it may be month inverse, or it may be year inverse. So anyone it may be, and these are the units you have to remember, but generally we are taking in the second inverse.